So what have we done so far? So far, we outline some general rules of probability theory. And with those general rules of probability theory, I can actually put that instead. Those rules of probability apply to every probability model. They're universal. Their value applies to everything in probability theory and in statistics. What is the classical probability model and what is the difference between probability models? The difference between probability models is the probability that is assigned at simple events. So if for example, let's go to a space, to a sample space. So this is an event space here. And let's say that this event space has a few simple events. Let's say that it has 5 simple events. Now, you know that if you do the experiment that actually this event space describes, one of these 5 outcomes will work. So this is 5 not S. So one of them will occur. More probably can occur, but you can observe at least one of them. Now, if you perform the experiment a second time, you may, the first time you may observe A1, the second time you may observe A2, the third time you may observe A5. Those are the events, and then you do the experiment the fourth time, and you observe A1. This is within the realm of possibility. And it's not something, when we say probability theory, and we say that one of the simple events will occur, we don't mean that you will observe constantly one event all of the time. You may continue observing one event a lot. For example, when you play the lottery, most of the times what will happen? Do you win or do you lose? You probably lose, okay? Well, so your loss occurs most of the time. And in this case, you will have 2 outcomes, win or lose. So most of the time you lose. That doesn't mean that you will not win. But it possibly means that you will not win within your lifetime. Because the probability of winning is so small. So that's actually what the problem describes. And the general model would say that the probability of S, actually the classical model says S is A1 union A2 union A5. And what that means beyond the symbolic language, that means that in plain English, when we execute the experiment, then we will observe the simple event A1, or we will observe the simple event A2, or we will observe the simple event A3, or the simple event A4, or the simple event A5. That's what will happen. And that's exactly encapsulated in this little equation. Now, 1 is the probability of the sample space, and therefore, since simple events are always exclusive. Why are they exclusive? Because they are simple. They describe only one outcome versus compounded events or composite events, which describe more than one simple outcome. So always simple events are exclusive. And therefore I can add the probabilities. And this allows me to derive a very simple rule. Why do I add the probabilities? Because we mentioned that the probability of the union, when the events are exclusive, is equal to the sum of the respective probabilities, and that's what I applied here. So all the probabilities of the simple events should add up to 1. Now, that's general, and that applies to every probability model here, modern or classical. The classical probability model makes the following assumption. uses one axiom, that all simple events share the same probability. The fact that it's classical and was built in the 16th century doesn't mean that we don't use it these days. We do use it these days. Actually, it is very desirable that when we do the lottery, when they produce the numbers, that of the winning numbers of the lottery, that is the exact outcome. Because if this is not the case, if not all simple outcomes are equally likely, then the lottery is biased. So some people, without even knowing, may have more chances to win than others. So there's a lot of experimentation that is being done to guarantee that all simple outcomes are equally likely in the case of the lottery. So the classical model is truly classical. It's something that is very true and very alive even today, and will be very alive to the ages. When you don't know what are the probabilities, when you have no possible way to evaluate the probabilities of the simple events, then you can follow the safe line and say that all simple events share the same probability. So if you are agnostic about the model, it's a good choice to assume that you have the classical model. And only if you see that what comes out, what you observe is beyond your expectations, then you can probably start changing the model or amending the model. So the classical model that was devised by Blaise Pascal assumes that all simple events share the same probability. Yeah, I'll push it up. Okay? So now that's better. Let me also do this thing and move it up even a bit more. Okay, so I have more space now. What is the classical model now? What does the classical model tell us? Well, this classical model tells us the following. Suppose that A is an event that is the union of these three simple events. Basically, A is the event that says A1 will occur, or A2 will occur, or A3 will occur. Under the classical model, what is the probability of A? Well, the probability of A is the sum of those probabilities, but all of them share the same probability, okay? All of them share the same. What is the probability that they share? What is the probability of each one of them? Well, all their sum should add up to 1. And there are 5 of them, all having the same probability. So what should be their probability? 1/5, okay? 0.2, or 1/5. I prefer to use fractions, because the fraction now, you see the denominator is giving me the total number of simple events I have. Okay? That's what it's giving me. Therefore, what is the probability of A here that I want to calculate? How many simple events do I have? I have 3 simple events. And in a total of 5, so you have 3/5 here. So this is exactly the rule. If I want to see it here again, 3/5 is basically the ratio of the number of favorable events divided by the number of all simple events. Actually, I would say favorable simple events. Favorable simple events, I need to... What do we mean by this? By favorable, we mean exactly this. So those are the favorable simple events that occur, that actually basically break down the composite event A. So the composite event A, which can be thought as a molecule, decomposes into the atoms A1, A2, and A3, and those are the simple events. So that's how it works in classical probability theory and in general in probability theory. That's true even for non-classical models. The classical model will simply make the simplification that all simple events share the same probability. So here is the classical model. And the classical model is very useful when we use the rules of counting in order to calculate probabilities. So let's use the rules of counting now and make and realize what we have done so far, implement what we have done so far. And push my screen a bit higher. And actually, let me go to a new page. Here. So what are the rules? What are these now? How are we going to use these rules? So let's think of the following problem. Suppose that we play poker. So we have a deck of 52 cards. Deck of 52 cards. Each poker hand contains 5 cards. Since some of you may not be familiar with cards, cards have 10 numerical values and 3 face values. So you have numerical values 1, which is ace, 2, 3, 4 through 10 are all numerical values. And then there are 3 face values, the jack, which is denoted by J, the queen, and the king. So in total you have 13 face values. And the entire deck is partitioned in 4 suits. So each card has a face value and a suit. The suits are these. It's the heart, the club, the diamond. Actually, those are red. Those 2 are red, and the diamond and the club and the spade. Now, I'm going to create something which looks like a spade, something like this. So that's the spade, and this is the club. My artistic skills are not that good. Those are black here. Yes. What? No, 13 face values. 13 4 times gives you 52. So for each suit we have all of the face values. Yes. And you can see, if you see the card has the face value in the corner and the suit under it. And half of the cards, 26 cards are black, 26 cards are red. Okay? So let's say we draw a hand of cards. So here is a simple probability model. Draw a hand of cards, a poker hand actually, we have to say which game you play. A poker hand of cards at random. I will explain to you what at random means. What is the probability that 3 cards, actually I would say exactly 3 cards among the 5 cards are red? Let's calculate this probability. Automatically, when we state this problem, this is a problem which has to be solved with classical probability theory. And with classical probability theory, your denominator is always the number of all simple events So you have to find which are the simple events, and the numerator is the number of the favorable simple events, and you will understand now what we mean by favorable. First of all, what are the simple events? To understand what are the simple events, you have to understand the experiment. So what do? We have a deck of cards and we throw 5 cards at random. The phrasing at random, that actually modifier that I'm using at random, means that all simple events share the same probability. That's why we put that statement there. Okay, when we draw cards, we don't replace the cards. So that automatically, the problem automatically assumes that you understand the basic mechanics of card playing, and therefore we don't replace the card. So we draw without replacing, correct? So what else do we do? Does the order count? No. The order doesn't count because we say a hand of cards. You can arrange the cards as you hold them in any way you want. So the order does not matter. So in a hand of cards for those reasons that we have mentioned is an unordered selection without replacement. And how do we call this? So this is a combination of a 5-hand card or 5 cards out of the 52. So what are the simple events here that I'm describing? We don't put them back.
No, not put back. Pull.
We draw for the 5 cards. No, let's not go there. Let's see what are the simple events. No, not how many. Which are they?
You need to get a red or a black.
Oh, the
No.
possible outcome.
What are the possible outcomes? What do I do? What do I perform? What's the description of the experiment? I draw 5 cards at random, okay? The experiment, the mechanics of the experiment is take the deck, draw 5 cards. All right? So what is the simple event? What is the simple outcome?
Like one drawing a key.
A random card, a simple event is just a hand of 5 cards out of the 52. What?
You have a brittle flesh.
Well, that would be a favorable event. Okay? So the simple event is just get 5 cards on your hand. And that's the generic description of the simple event. So those are combinations. So the simple events here are combinations of 5 cards out of the 52 because I draw them without replacement and the order does not matter for the reasons we explained. Furthermore, the problem is saying you draw at random, and that automatically means that you're in the classical probability regime. All simple events share the same probability. So this is the rule here that applies. Okay? That rule applies. So how many simple events do we have in total? We have a pool of 52 items and we draw 5 out of them, combination of 5. How many of them do we have? Now you go to the rules of counting. It's 52, choose 5. So the number of simple events, for this reason, okay, so therefore, the number of simple events is equal to 52, choose 5. Now we have to see what is the favorable event. What is the description of a favorable event? We say exactly 3 cards among the 5 cards are red. Did you see that I squeezed exactly? Initially I was writing 3 cards among the 5 cards are red. we'll see the difference between the two. Let's play with the exactly. So what is the favorable event? A favorable simple event. Exactly three of the cards are red. And the remaining two, what should they be? Black. Because I said exactly. Okay, so a favorable event or a favorable simple event consists of drawing a hand of 5 cards and 3 of them are red and 2 are black. Okay? Now we have to find the number of the favorable events. And that's something we need to, I can push it a little bit up. Okay? Yeah, that's what I'm going to do. Push it up. Okay, so let's see how many are the favorable events. So a favorable event consists of putting, let's see, to understand how many favorable events you have, basically you have to construct the favorable event. So how would you construct it? You would look in the deck of cards and find 3 cards. 3 are red. So the first part is the selection of the 3 red cards. The remaining part is the selection of the 2 black cards. So first we have to see in how many ways we can select the 3 red cards. That's part of experiment 1. And then the selection of the black cards. Do you understand the difference between the two? The simple event has no restriction. The favorable event has restrictions because it has a specific property. 3 cards are red, exactly 3 are red. Therefore 2 must be black. So to form the favorable event, we first need to select the 3 red cards, and then for every selection of the 3 red cards, we have a selection of 2 black cards. So let's see, in how many ways let me not use experiment. Selection of 3 red cards first. How many red cards do we have? We have 26, and we select the 3 cards in the same way we select for the generic simple event. That's very important to understand that the rules that apply for the denominator exactly apply for the numerator, the rules of the selection. So, rules of selection for generic, simple, and favorable simple events must be the same. And that's because you can't divide apples by oranges. If you use one way to select in the denominator and a different way to select in the numerator, then you divide things that are not exactly the same. So you will end up with the wrong result. That's very critical. So the selection of the 3 red cards is a combination, again, because we use combinations for the denominator, is a combination of 3 cards out of the 26 red cards. So then we use 26, choose 3. This is the number of ways to select the 3 red cards. That's the first part. Now you come to the selection of the 2 black cards. It's exactly what I was doing with the pizza. I select the number of crusts, the appropriate crust, and I can do it in so many ways. And then I select what we put on the crust, the cheese, for example, or the sauce. I can do it in so many ways. And how many total outcomes do we have? We just multiply the outcomes of the selections of the red cards, of the ways we can select the red cards, and of the ways we can select the black cards. Is it clear? So in how many ways can we select the 2 black cards? 26 choose 2, because we have 26 black cards. Ways to select the 2 black cards. So in general, the number of favorable events is equal to how much? 26 choose 3 times 26 choose 2. So what is the probability now that exactly 3 red cards are contained in the 5 card hand? Mm-hmm. Yes. Fine. So this is 26 choose 3 times 26 choose 2 divided by 52 choose 5. And you don't make any further calculation. That's the end of the story. Just leave it like that, because if you try to compute it, we can't compute it. I'm not going to spend time computing each one's results. Neither will I do, nor will the grader do. So just leave it like that. It's easy, crisp, clear. The rest is for calculators. No. You can use your phone if you need to calculate, 156 times 251. Okay, but the needs for calculators are very minimal in this first part of the course. You may need them later on with statistics when we have fractions and there's composite fractions and you need to do some more elaborate algebraic calculations to find the value of the statistic, because if you don't find the value of the test statistic, then you will not be able to derive a conclusion. But right now you don't need. Any questions so far? So this was the first problem. Let's see one additional part. You see that when I was doing the phrasing of the problem, I want to put the word exactly. And I put the word exactly because I only wanted to arrive at a very simple, not simple event, simply in terms of the of its formulation, composite event. Nearly A was a composite event because it had so many simple events. At 26 choose 3 times 26 choose 2 simple events. Why did I put, had I not put the word exactly, what would that mean? And here is one part that you have to be very careful. Be very careful about the statements you make and about the statements you read. Because if you don't understand them correctly, if you misinterpret them, then you solve part of the problem or half of the problem. Let's ask your friend.
Wouldn't it mean exactly? Couldn't it mean that you would have 4 cards?
You can have 4 red cards or 5 red cards. So you could have had more simple, more composite outcomes. Okay, now let's solve the problem this way. And now you will see the application of the rules of probability if we solve the problem by basically eliminating the word exactly. The mechanics are pretty much the same. So suppose now that you want to calculate the probability that 3 red cards are contained among the 5 cards. So that's the problem. We already know part of the solution because we don't have to recalculate the number of favorable simple events. We've done this before, yes. We will use unions, yes, but let's see, let's go there slowly. Let's go there slowly. So when we say 3 red cards are contained among the 5 cards, that means that we can have 3, exactly 3, or exactly 4, or exactly 5 red cards among the 5 cards. What are these events that I just described? Exactly 3, or exactly 4, or exactly 5. Are they exclusive? Yes, they are exclusive because each one rules the other out. Okay, so the 3 red cards, which I would call are contained among, now you will see me using a little bit more elaborate, some more notation, the 5 cards. I would call this event B, and you see I put the notation here, I call it B, and I call B1 to have exactly 3 red cards are contained among the 5. B2, it's exactly 4 red cards are contained among the 5, and B3, I'm using some notation to simplify the language and write less things. Exactly 5 cards are contained among the 5 cards. So B is the union. Why do I call it union of these 3 events? Because I used or. That's why. Or means union, and means intersection. And these are exclusive. So now the probability of B, which is what I want to calculate, is equal to the sum of the probabilities of the respective sets. And now I have to calculate the probabilities of the respective sets. Well, we've calculated the probability of B1. What is the probability of B1? We calculated that was before 26 choose 3 times 26 choose 2 divided by 52 choose 5. So what is the probability of B2? You don't have to repeat all the arguments and write all we wrote before. You can say likewise. Or in a similar fashion we derive that. What is the probability of B2 now? You have exactly 4 red cards. So it will be 26 choose 4 times 26 choose 1 divided by 52 choose 5, correct? And finally, the probability of B3 is what? 26 choose 5. That's it. No black cards there. Divided by 52 choose 5. And the probability of B is just sum all of these guys, and that's how I would write it just for illustration. I would make a big fraction. I would not attempt to calculate this fraction. And that's the end of the story. Problem solved. Any questions? Yes. The probability of B2 or B3, 26 choose 5 divided by 52 choose 5. Why 26 choose 5? Because you want 5 red cards. You want all the cards in the hand to be red. Yes.
Where does this account for the fact that as you draw the cards, the number of total cards and the number of red cards decreases?
That's a good question. It accounts in the way we construct factorials. I mean, in the way we construct actually this binomial coefficient. The formula 26 choose 5 takes that already into account. And I can show it to you a little bit, but I don't want to elaborate a lot. Let's see in how many ways let's see why we have 26 choose 3. That will make it easier to show it. Why do we have 26 choose 3 choices for choosing the 3 red cards among the 5? Well, for the first red card, how many choices do you have? You have 26 choices, okay? Now, once you have drawn this red card, this card is out of the pool because you draw one. How do you draw? Without replacement. So you have one red card less to choose from. So how many red cards do you have now to choose from? For your second selection, you have 25. And how many do you have for your third selection? 24. Okay? So it seems that you have, if you draw the 3 cards successively, the 3 red cards, you have 26 times 25 times 24. Now what does that mean? First card, second card, third card. What is this? This is an array of cards. And what is an array? An array is an ordered selection. But when you hold them on your hands, you don't care about the arrangement. You care about what you hold. The result, 26 times 25 times 24, is an ordered selection. So that's the number of ordered selections. So this is the permutation of 3 cards out of the 26. This is the number of permutations of 3 cards out of the 26. So now how do you go from the order into the non-order? Suppose that you have 3 cards here, which are red. You have red ace, red 3, and red 4. You see, here's your first card, your second card, your third card. But if you change them and you put this one first and this one last, what is in the hand doesn't change. In how many ways can I permute those 3 cards among them? 6, which is 3 factorial. So that number has to be corrected by 3 factorial, which is the number of permutations of the 3 items. So now let's look what we have here. (26) times 25 times 24 is 26 factorial divided by 23 factorial, okay? Why? Because the numerator is all the numbers, the product of all numbers, integer numbers from 1 through 26. The denominator is the product of all integer numbers from 1 through 23. And of course, if you simplify, if you do the simplification, you will get from here, you will get 26 times 25 times 24. Correct? Well, let's fix this a little bit. What's the 23 factorial? The 23 factorial is actually 26 minus 3 factorial. And this is exactly what I wrote, 26 choose 3. Something happened here. Do we all have it? Is it clear now? How it's been done? So that's the answer. So it has taken already that into account. Because I said, once you draw the first card, you have a pool of 25. So it's all been figured, it's all been priced in, to use an expression of the day. Any other questions? No questions? So what probability do you want to calculate with poker? You don't play poker? I don't play poker. I just use it for problems. Four of a kind? Okay, that's interesting. What does mean four of a kind? All the same cards, the same numerical value, okay? The same value from 1 through 13. So let's say, what is the probability of four of a kind? That's a nice problem. What's the probability of drawing four of a kind? Well, already you know what is the number of all simple events, 52 choose 5, so let's keep it. So here is what we need to work on the number of favorable events. So let's work on the number of favorable events here. We said four of a kind. So how many choices, how many kinds do we have? We have 13 kinds. So let's pick one of them. Let's say, what is the probability to have four aces among the 5 cards? That's not the solution of the problem, it's part of the solution of the problem. If you can't solve that, I guarantee you one thing, you can't solve the problem. Because if you can't solve the easier version of the problem, you will have significant difficulty to solve the general problem. So try the smaller problem first and see what you can do. So what is the probability that I have 4 aces among the 5 cards? I try to find a number of favorable events, favorable simple events. How can I form the favorable simple event? Let's draw from what we did with the red cards before. We wanted the 3 red cards among the 5 cards. So first we show how many ways we can select the red cards. Let's see now how many ways we can select the 4 aces to place them in the 5 card hand. How many ways can we select the 5 aces?
4. The 4 aces.
We have 4 aces, and we want all the aces to be in the 5 card hand. How many ways can this be done? I can't hear. Can you please speak loud? What? Why 4 different ways? How many aces do you have in the deck of cards? You have 4. And you want the four aces to be in the 5 card hand. So once you have the 4 aces in the 5 card hand, how many aces are left in the deck? None. So in how many ways can you put the aces in the 5 card hand? Just one. You got to put all the aces in the 5 card hand. You run out of aces. That's why I ask you how many aces are left in the deck of cards after you have already put the 4 aces in the deck in the hand. There is only one way, because you exhaust all of the aces. So only one way. And why did some of you said 4 ways, which wasn't correct? Probably you thought about the order. No, here the order doesn't matter. We have a combination. So selecting the 5 card, only one way to select the 4 cards of the same kind All right? So now suppose that you have selected the kind. You've chosen all the cards of the same kind. But you did that for one kind. The hand, the favorable hand needs one card more. So that is being selected at random. How many choices do we have? We have already taken the aces out. So now we have how many cards left? 48. 52 minus 4, that gives us 48. And the remaining card is any one among the 48, okay? We have no restrictions for the remaining card. 48 choose 1 will give you 48. Okay? The correct answer is 48 choose 1, but it will give you 48 if you do the algebra. Okay? So, we have one way to select the 4 cards of the same kind and 48 ways, which is 48 choose 1, to select the remaining card. That's for one suit. So that applies for one suit. Now we have 13 suits. We have 13 kinds. So this process is can be repeated 13 times. Each per kind. So the number of favorable events is equal to 13, the number of kinds, times 1 times 48 divided by 52 choose 5. So, in short, you have 13 times 48 divided by 52 choose 5. Any questions? Yeah? To calculate it? Anna? I don't have a calculator that can do that. If anybody has a scientific calculator, it's going to be a small number. Yeah, but I could have done with the union. You can say A is select 4 cards of one kind, of same kind. Yes, of same kind in the 5 card hand. And then you would have A sub I select 4 cards of kind I, and this will be the same, and then A is the union of A1, A2, or to A13. And these are exclusive events. And actually the probability of A sub I, if you look, is equal exactly to this term here. 48 divided by 52 choose 5, which is what I calculated here at this part. This part gave me this calculation. Actually, this part. The 13 is because we have 13 kinds. The kind is the numerical value. No. The 48 is for the 5th card. So the 48 accounts for the 5th card. The 13 accounts for the number of kinds. The kinds are the numerical values. Ace, 2, 3, 4, 5, and so on. Jack, King, and Queen. Any further questions? If we have no further questions, I'll just stop it here.